Expedition Everest is a really good ride in Disney World's Animal Kingdom. The part that's most scary to me is when it starts going backwards. I don't really enjoy that part of the ride, but that's part of why I chose it for this question. So, A, when is the rider moving forward? When is the rider moving forward? So this is a velocity time graph. And if we read carefully, it says meters per second forward. So that means that anywhere where the graph is above the time axis, this ride is going forwards. For example, at the beginning of this segment of the ride, whatever segment they're talking about, it's going at 10 meters per second forward. And then a few seconds later, it looks like the velocity has decreased to 5 meters per second, but it's still going forward. And then at 8 seconds, for example, the velocity is 20 meters per second forward. So at all of these times, it looks like up until 12 seconds, the velocity is always going to have a positive forward value. So the answer to part A is from 0 to 12 seconds. B, when is the rider moving backwards? So this is the scary part of the ride. You don't see where you're going because it's going backwards. And on this velocity time graph, you would be looking for segments of the graph that are below the time axis. So they'll have a negative value for the velocity. So that looks like it's from 16 to 18 seconds. For example, at 18 seconds, the velocity would be negative 10 meters per second forward. So that means it's going backwards. Part C. When is the rider at rest? So we are looking for zero velocity. We're looking for a zero velocity for when the rider is at rest. And that happens from 12 to 16 seconds. So don't think that from 3 to 5 seconds the rider's at rest, because from 3 to 5 seconds, even though the line's horizontal there, it actually has a value of 5 meters per second forward. So it is moving at that segment. All right, D. When is the rider speeding up? When is the rider speeding up? So for speeding up, we are looking for numbers that are getting higher in magnitude. So the first one I identify would be from about 5 to 8 seconds. 5 to 8 seconds. Here, let me go with some green highlighting. Speeding up. Speeding up because if you read the numbers on the axes, it's at 5 meters per second, and then it goes up to 10 meters per second, to 15 meters per second, to 20 meters per second. As the numbers are getting higher, it is speeding up. However, that's not it. There's another section where it's actually speeding up, and that would actually be this last section. When it's moving backwards, actually, it's getting faster going backwards. So that's what makes it really scary. At 16 seconds, it's actually at rest at 16 seconds at 0 meters per second. And then it speeds up to negative 5 meters per second. And then speeds up to negative 10 meters per second, which is even faster because the magnitude of these velocities are getting larger. So I'm going to say and then slowing down. So we'll just kind of switch colors here. Let's go with black. So slowing down, you're looking for the opposite. You're looking for numbers getting smaller in magnitude for the velocity. So the first section I'm identifying is the first 3 seconds. So for the first 3 seconds, I see it starts at 10 meters per second, then drops down to 5 meters per second. So it got slower. I see another section there from 8 to 12 seconds. It looks like it's gotten slower. All right. F. When is the object at rest? No, sorry. When is the object moving at constant velocity? We already answered the question when it's at rest. When is it moving at constant velocity? So I pointed it out a bit earlier, actually. That's this little segment here where the velocity is staying at 5. The velocity is staying at 5 meters per second forward. So it's not changing for that chunk of time. So it's a constant velocity there. So that looks like it's from 3 seconds to 5 seconds. All right, G. So now we're going to get into some calculations here. I'm going to try to clean up the graph a little bit. I've highlighted a bunch. Just, okay. Determine the acceleration for 8 to 12 seconds. So 8 to 12 seconds, I'll just put a couple points here. Here's 8 seconds, and here's 12 seconds. And those 2 points are joined by a straight line. So this is going to be a uniform acceleration. It's slowing down. And we want to calculate the value for that acceleration. So we can calculate the slope of that line segment, which is rise over run. In this case, the rise is negative. The function's decreasing. So it goes from 20 down to 0. So the rise is actually negative 20. And the run, so it goes from 8 to 12, so the run would be 4. Here, I'll say 12 minus 8, just so you know where the 4 came from. So it's negative 20 divided by 4, and that would be negative 5. The units of acceleration in this case would be meters per second squared. The direction is forward. It's a negative answer forward, or if you wish, you can say it's a positive answer backwards. Okay, and now H. Determine the displacement from 8 to 12. So the same interval of time. Now we're determining the displacement. And this one is might not be as intuitive. But to determine the displacement using a velocity time graph, we actually calculate an area. So I drew a line down at 8. So I'm going to shade in the area we want. So area between the function and the time axis. So this area will actually give us a displacement. So that's a shape I'm familiar with. It's a triangle. So the area of a triangle is base times height divided by 2. The base of that triangle, it goes from 8 to 12, so the base is 4. The height goes from 0 to 20, so the height is 20. and divided by 2. Actually, I can add this little step to maybe point you towards understanding why we're calculating the area here, but maybe not fully. The 4, which was the base, that's on the time axis. The base is on the time axis, so the units would be seconds, 4 seconds. And then the height, so the height is vertical. It corresponds to the velocity axis. So it's 20, but the units on the velocity axis are meters per second forward. So what happens when you multiply, if we just look at the units here, so what happens if we multiply seconds by meters per second? Well, then those seconds actually cancel out, leaving you with just meters. So those are going to be the units at the end, which are the units of displacement. And the direction is going to be preserved as forwards. And I'll just do the numbers now. So 4 times 20 divided by 2, that turns out to be 80. 80 divided by 2, which is 40. All right, so that's how you get displacement on a velocity time graph. And finally, question I. What is the physics term used for what is happening at the cusps, or what is happening to the rider at the cusps of the graph? The cusps are the sharp points. So there's a physics term. So, for example, the cusp right in the middle. So it's accelerating in a positive direction, and then suddenly it changes its acceleration to go in the negative direction. That's a sudden change of acceleration. So what I'm looking for is, do you know the word for a change in acceleration? And that word would be jerk. The rider is experiencing a jerk at 8 seconds and at all the other cusps, but it looks like the biggest jerk is at 8 seconds. All right, that's the Expedition Everest graph.